Hi, everyone. So today I'll be talking about under-constrained symbolic execution, which was joint work with my advisor, Dawson Engler at Stanford. The two main contributions of this paper are a technique and a tool for finding deep bugs in real, open source C and C++ code. This tool requires very little manual effort, and in particular, doesn't require any manual test cases or a functional specification to be provided. Now, I should note that the types of bugs that it finds may have security implications. The tool does not specifically identify which bugs are for sure exploitable, though there's one aspect of the tool that I'll get to at the end of the talk that does try to identify these vulnerabilities. And so the types of bugs that it finds are memory access and heap management errors, assertion failures, and divisions by zero. And using our tool based on this technique, we found 77 new bugs in BIND, OpenSSL, and the Linux kernel, including 2 OpenSSL denial of service vulnerabilities for which advisories were issued in the past year or so. We also found 14 relatively minor Linux kernel vulnerabilities. So current practice for preventing bugs from reaching end users falls roughly into 4 categories. We have code reviews, we have safer languages such as Java that try to avoid some of the more error-prone language constructs such as pointers. There's traditional manual regression testing, and then there are a variety of static analysis tools such as Coverity and the Clang Static Analyzer. However, despite all of these techniques, bugs are still everywhere. So one technique that has shown some promise in finding the types of bugs that are missed by those other techniques is symbolic execution. And with symbolic execution, the idea is that we provide symbolic rather than a single set of concrete inputs. And using these inputs, a symbolic execution tool will conceptually explore all possible execution paths through a program and consider all possible inputs. And these tools accurately track all memory values up to a single bit of precision. And then along each execution path, the tool sees whether any input values could cause that execution path to crash. And if so, it reports a single set of concrete inputs to the user that can be used offline to reproduce and then fix the bug. And this work builds upon the KLEE tool, which is prior work from OSDI in 2008. So here's a simple example of how symbolic execution works. Here we have this function foo that accepts a single integer argument x. Let's assume that our symbolic execution tool is running some program. It gets to this function foo, and it passes in a symbolic value for x. So this is any possible value representable as a 32-bit integer. So execution begins with this if statement. And here we're comparing the symbolic value x against 0. So it's symbolic. We don't know whether it has the value 0 or not. And then, so rather than choosing either the true or false branch, the tool conceptually forks execution. Sorry about that. And considers each path independently. And so on the left-hand side here, we have the case where x is non-zero. So here we take the true branch. So the next statement that is executed is this division operation, x over 10. Whenever division is executed, the tool checks to see if the denominator could be 0, since this would trigger a floating point exception and crash the program. So the tool looks at this division. It says, OK, the denominator is 10. It's clearly not 0, so this division is OK. And on that path, we return from the function. On the other path, we have this division 10 over x. And so once again, the tool looks at the denominator and says, can this denominator be 10? Well, since we took the else branch, x actually has to be 10 in this case. And so we always have an error on this path. And so along this path, the tool would report an error to the user along with a concrete test case where x is assigned the value 0 to allow the user to reproduce it. And then it would terminate this execution path and only continue executing the other path which did not crash. So the main problem with symbolic execution is scalability. It suffers from the well-known path explosion problem, since the number of distinct execution paths through a program is roughly exponential in the number of if statements. We also have issues where individual execution paths may be very long and complex, or even infinite, in which case we run right into the halting problem. And finally, symbolic execution tools use SMT solvers for a lot of their logic. And these queries are very expensive, and so a significant percentage of execution time for one of these tools is typically spent waiting for these queries to be solved. So the solution we propose in this paper is under-constrained symbolic execution. And the idea here is to directly execute individual functions within a program symbolically rather than doing a whole program symbolic execution. The goal being that if we're executing less code, then we're exploring fewer paths and they're also less complex. However, when I say individual functions, if a function performs a function call to another function, we do actually follow this call and execute that function. So this is still inter-procedural symbolic execution. We just begin at some arbitrary function boundary rather than at main. And so using this tool, we're able to test previously unreachable code deep within a program by just jumping directly to that function. This technique does introduce two primary challenges. The first is that whole programs often accept just very simple inputs from file descriptors or command line arguments where they're just simple byte arrays. Functions within a program often accept complex inputs, pointers to data structures. And so we have to be able to generate these data structures. The other issue is, as the name implies, under constrained, we're missing constraints on these inputs. When you call a function somewhere within a program, typically there's some set of preconditions on that function. For example, if it accepts a pointer argument, there may be a precondition that that argument cannot be null. And so our tool doesn't know these preconditions since it doesn't require the user to specify anything. So it spends some time exploring infeasible execution paths. And along these paths, when it finds errors, these are considered false positives. So in this paper, we discussed the UC-KLEE tool, which is our implementation of under-constrained symbolic execution that extends the KLEE tool, and it runs on LLVM bitcode that's compiled from C and C++ source. And it automatically synthesizes complex inputs using a technique based on lazy initialization, which is also used in Java Pathfinder, which is a Java-based symbolic execution tool. However, unlike Java, C and C++ support arbitrary typecasting and pointer manipulation, so our tool has to support all of these features as well. Finally, our tool accepts a user-specified input depth bound. So as it generates data structures to use as input, the user can specify how deep these data structures should be. And in the literature, that's called k-bounding. So lazy initialization works by initially marking all inputs as potentially being pointers. Since in C and C++ you can cast any value to a pointer, we don't know a priori whether a particular input will later be used as a pointer. So we assume that anything may be a pointer, and we initialize it to this unbound state. Then the first time we dereference one of these unbound pointers, we allocate a new object to satisfy this dereference. We then bind the pointer to this new object by adding a path constraint that this pointer is equal to the address of the new object. And then on subsequent dereferences, this pointer will just map back to that object that we allocated the first time. Now here we assume no aliasing. We could also consider cases where when they dereference one of these pointers, it maps to existing objects. But we found that for our workloads, this led to more false positives than it did improve the analysis. But for certain workloads that require cyclical data structures, we may revisit this decision. So here's a simple example of how lazy initialization works. Here we have this function listSum that iterates over a linked list and returns the sum of the elements. And let's assume that it's passed in an unbound symbolic input for this argument n that points to the head of a linked list. So execution begins. First we assign 0 to sum. Nothing special happens there. So let's consider now this loop header. So here we're comparing n against 0. Just as in the earlier example, rather than choosing either true or false, the tool forks execution and considers each possibility. So on the top here, where n is 0, this is effectively representing a linked list of length 0. And so on that path, we don't enter the while loop, and we simply return 0. So let's consider the more interesting path where n is not 0, and execution enters the while loop. So the next instruction that's executed is this dereference of n. We're reading this val field from within n. And so n is an unbound symbolic pointer. So to satisfy this dereference, UC-KLEE allocates a new object that we refer to as UC node 1, UC for under constrained. And this object is itself initialized to contain unbound symbolic inputs, so that if any pointers within this object are dereferenced, we can start to build this data structure recursively. And that's sort of the key behind lazy initialization. We now bind n to this new object by adding the path constraint that n is equal to the address of UC node 1. So execution continues. We read this symbolic value next from UC node 1 and assign it to n. Then we return back to the loop header. Here we're comparing the current value of n against 0. So n holds the symbolic value UC node 1.next. And again, it forks execution since it could be 0 or non-0. So in the middle path here, we're effectively, where UC node 1.next is 0, we're effectively representing a linked list of length 1. And on that path, we'll break out of the while loop and return the current sum. On the other path, which we'll consider here, we enter the loop once again, where UC-node1.next is non-zero. We'll now dereference this pointer n. And so since UC-node1.next is an unbound symbolic pointer, we once again allocate another new object that we'll refer to as UC-node2. We'll then bind UC-node1.next to this new address, to this new object by adding the path constraint that UC-node1.next is equal to the address of UC-node2. Execution continues as before. We read this next field. We return once again to the loop header. And so this would continue ad nauseum until the tool reaches the user-specified depth limit. And so here we'll assume that the user specified a depth limit of 2, and we'll stop at a linked list of length 2 and break out of the loop, if my laptop will cooperate. Okay, so in this paper, we discussed 2 use cases. The first is equivalence checking in the context of patches. And here we're comparing essentially yesterday's code against today's code after applying some patch. And the goal is to detect whether or not this patch introduced any new crashes. And we discussed other use cases for equivalence checking in earlier work from CAV 2011, but here we're focused only on patches. So patches are a well-known problem. Here we have Grumpy Cat lamenting the fact that we start with this large corpus of bugs, we try to fix one, and we end up with more bugs than we started with. And I think everyone in this room is probably familiar with this. The other use case we look at in this paper is general bug finding, where we look at a single version of a function, and we apply rule-based checkers on top of symbolic execution. And here we look for specific types of bugs, such as memory leaks, uses of uninitialized data, and unsafe uses of user input. And our tool provides a simple interface for adding new checkers in addition to these. So equivalence checking essentially works by calling 2 versions of a function and asserting that their outputs are equivalent. In reality, there are 2 aspects to equivalence as we define it in this paper. The first is value equivalence, where their outputs in terms of return values or any arguments that are modified or globals, as well as any system call effects, are all equivalent between 2 versions of this function. The other is error or crash equivalence. So as I mentioned, inputs to individual functions typically have some set of preconditions, and within our tool, these are unknown preconditions. When we're doing cross-checking or equivalence checking, we don't know what these preconditions are, but we do know that in most cases, the 2 functions have the same set of preconditions. So here we're interested in cases where one version of a function crashes, but the other does not. If they both crash, we assume that this means that that those inputs that caused the crash violated those preconditions. And so we do not report an error in that case. Now in this paper, we're only concerned with error equivalence, where the version of a function after a patch is applied crashes, but the old version does not. We're not actually looking at value equivalence, though our tool does have this capability. When we're performing equivalence checking, we're doing this on a per path basis. And if our tool exhausts all possible execution paths through a function, then it has effectively proven that the 2 versions of that function are equivalent up to the input bound that we explored and with certain caveats that we describe in the paper. And this is a pretty strong guarantee that's not possible with most other tools. So we evaluated equivalence checking on BIND and OpenSSL, which are 2 mature security-critical code bases, each of about 400,000 lines of code. We looked at 487 patches from BIND and 324 patches from OpenSSL, and we ran our tool for 1 hour on each of these patched functions. And in this experiment, we discovered 10 new bugs, 4 in BIND and 6 in OpenSSL, including, as I mentioned, 2 OpenSSL denial of service vulnerabilities. We also verified that 67 functions from BIND and 48 from OpenSSL do not introduce any new crashes, again with certain caveats. And here we used a maximum input size per object of 25 kilobytes, which is a pretty substantial input size. So here's one of the vulnerabilities that we found in OpenSSL. Here we have this do SSL3 write function that's used to send an SSL message. The first thing this function does on line 1 is check whether the write buffer is null. And if it's not, then it allocates it on line 2. When execution reaches line 6, the code checks to see whether an SSL alert is pending. And if it is, it sends that alert before the current message. And it does that on line 7. Well, it turns out that this SSL dispatch alert function pointer eventually recursively calls this do SSL3 write function. And at the end of this function, if this one option is being used, it will actually free the write buffer and set it back to null. So when execution returns back to line 8 after sending out the alert, this write buffer that we checked on line 1 has now been set to null again after the check. And so then when execution reaches line 14, we have a null pointer dereference. Now this bug occurred on an uncommon code path. Both this SSL mode release buffers option and an alert has to be used, and an alert has to be pending simultaneously. This type of uncommon path is typically missed by regression testing, and it's probably why this bug was not found. However, this option is used by Apache mod SSL, so we believe it did affect a fair number of servers. As I mentioned, functions inputs typically have some set of preconditions that are unknown to our tool, and we explored two partial solutions to this problem. The first is a couple of automated heuristics that try to identify which errors are most likely to be true bugs and not false positives, and we also allow the user to specify manual annotations to silence errors after they occur. This is in contrast to many tools that require the user to do a bunch of work up front before they can even use the tool, like in model checking. Here, the user can use our tool without any effort up front, and then on the back end, if it reports false positives, they can silence these. In practice, we found that simple annotations can actually silence many errors. And here's one example. Here we have this ISC region compare function from BIND that looks at two memory regions and compares them. And a memory region is just a base pointer and a length. However, our tool does not know that this base pointer and the length have anything to do with one another. So this memcomp call on line 10 returned a lot of out-of-bounds read errors that are actually all false positives because the code properly checks the length on line 8. And so we silenced this false positive with a simple one statement here, the invariant that the length of one of these memory regions is less than or equal to the size of the object pointed to by the base pointer. And so this one line applies to all instances of this data type, ISC region T, everywhere in the code base. So we only had to specify this once, and it silenced 623 errors, which was about 7.5% of all of the errors that we found for BIND. Total, we wrote about 400 lines of manual annotations for BIND and about 60 lines for OpenSSL, which we believed was reasonable effort relative to the sizes of the code bases and their importance. The other use case we look at in this paper is general bug finding, where we look at a single version of a function in isolation, however, still with lazy initialization. And we wrote 3 individual checkers that look for specific types of bugs. We wrote a leak checker, an uninitialized data checker, and a user input checker that are conceptually like Valgrind, except we apply them to all execution paths through a particular function. And we evaluated these checkers on over 20,000 functions from BIND, OpenSSL, and even the Linux kernel. And we found 67 new bugs, including 37 memory leaks, 19 uses of uninitialized data, and 11 unsafe uses of user input, all of which were in the Linux kernel. So the user input checkers, probably the most interesting of the 3, especially to this audience. When we say that an input is under-constrained, it's because we're missing these preconditions on a function. There are a subset of these inputs where we actually know that any input is possible, and these are inputs that originate from the outside world, where an attacker can specify any possible value. And so we refer to these inputs as fully constrained. And so the checker keeps track of whether each symbolic byte is under-constrained or fully constrained. And then if an error occurs that is caused by one of these fully constrained values, it will annotate the error report with this unsafe input flag to tell the user to look at this more closely, that it may be exploitable by an attacker. However, it suppresses this flag if the code at any point compares one of these fully constrained values to some other value in order to try to sanitize it. So our code can't tell whether or not a value is properly sanitized, so it assumes that anything that was at all sanitized was correctly sanitized. And so here we have a trade-off between having more false positives, where we show this flag even though it was sanitized, versus hiding true errors. And we opted for the latter in this case, but it would be really easy to change our tool to report all of these errors if they were of interest. So we specified which inputs were fully constrained using very simple C annotations. For Linux, we annotated the get user and copy from user functions as returning fully constrained values, as well as all arguments to system calls. For BIND, there's this ISC buffer function that's used to extract individual characters from network inputs. And then finally, for OpenSSL, we used a trick that we credit to Andy Chow from Coverity, where code that swaps bytes from network byte order to host byte order is typically operating on network inputs. And so we have any values that are returned by these byte swap functions, and as we mark them as being fully constrained. So here's an example bug that we found in the Linux kernel using this checker. Here we have this, and this was in the VMware VMCI driver, which is used for communication between the host OS and the guest OS. And this particular function is used to send a datagram from the host to the guest. And this function is called using a datagram that was read from user space on the host via copy from user. It then reads this size field from within the datagram, and without checking it, uses it as a size argument to memcopy. And as a result of this bug, the user could send up to 69,000 bytes of host private kernel memory to the guest OS. And if this bug signature looks familiar to you, it's because it's almost identical to the OpenSSL Heartbleed vulnerability from last year. And so while this particular vulnerability had very little impact, because it doesn't involve network inputs, it's only code running on the host OS communicating to the guest, and we typically trust the host more than we trust the guest anyway. This does illustrate that this tool can find the types of bugs that in other contexts may have severe security implications. So I've briefly discussed under-constrained symbolic execution, as well as two use cases, including equivalence checking in the context of patches, and general bug finding using these rule-based checkers. And I've also summarized our experimental results on BIND, OpenSSL, and the Linux kernel. And at this point, I'd be happy to take any questions.
So please come step up to the microphone. As usual, state your name.
Please, not everyone all at once.
While you're thinking, let me ask you one or two myself.
Sure.
So one thing that I find really fascinating about this work is looking at patches. I wonder if you thought anything about maybe fuzz testing of patches. So as a kind of a dumber, bruter force version of the symbolic execution, do you think it might be possible to get maybe not as good results, but some useful thing? What might the challenges be?
So I mean, there are various types of fuzzing, and the smarter ones tend to use symbolic execution anyway. So I from your question, it sounds like you're talking more about the just dumb fuzzing where you're just coming up with some random input, let's say. So the issue there is you're typically doing that on a whole program, and it's difficult to even find values that will get you to the function where the patch was applied. It's actually very difficult, and even with general symbolic execution, to find a path from main down to some function that you care about. And that was one of the reasons that we decided to step away from that problem and just try jumping directly to these functions.
Hi, I'm Pei Wang from Penn State University. Actually, your work reminds me of a paper published earlier this year. I think they called document assisted symbolic execution. What they did is they extract like arguments from the human written documents and make constraints on the input based on the documents, so they can make the symbolic execution more scalable. So how would you compare your work with theirs? Like, which one do you think fits the real field development better? Or does either of them has particular weaknesses or strengths?
So I don't view that other technique as an either or. I think that's completely complementary to our approach. We know nothing right now about the preconditions to these functions, so if we could somehow read over the documentation and automatically infer these, that would be fantastic. That would absolutely help us tremendously. So I'd say they're completely complementary.
Okay, thanks.
I'm Christoph Kern with Google. I have a question about the annotations that you add to state these invariants. I guess there's a possibility that the invariant you manually state is actually wrong,
Yes.
and therefore masks a bug that's actually there. So what do you do to validate these invariants? I mean, can they be runtime executed in test mode, for instance? Are they executable code that could run in a debug environment, that kind of thing?
You could. We did not do that. But yes, it's just C code. So you could compile it and run it and just kind of inject them into a production environment or someplace where the whole program is running to see whether or not they hold up. Yeah, that would actually be a nice way of validating them.
So is there actually also a way, perhaps for the symbolic execution, to recognize that it can get into a state where the invariant is wrong? Or would that sort of self-referentially defeat the purpose of having it?
I think in our case it would defeat the purpose, but you could use whole program symbolic execution to check these, or to even give you a starting place to feed into the more scalable version.
Hi there, I'm Trent Jaeger from Penn State. So I wondered if you could comment on how your tool affects the search space, the path explosion, and the path length. So I guess with the path length, you have the user-specified restrictions. I was wondering if you could take advantage of things like fixed point analysis or something like that in symbolic execution. And then for the path explosion, I mean, you're just moving around where the starting points are, but I didn't get a clear sense of how this restricts the explosion if eventually you'll have to hit the same code.
Sure. So clearly if you're executing a subset of a program, there are going to be fewer paths than the whole program. That small subset may still be infeasible. There may still be too many. And for a fairly substantial percentage of the functions we ran on, we did not exhaust all execution paths, even within an hour, for that reason. There are a number of heuristics that we did use for the search space. So we do prune a lot of redundant paths and paths that cannot reach code that was affected by the patch. So we have this whole static pass that goes over two functions and identifies which basic blocks changed between the pre-patch version and the post-patch version, and only execute paths that can reach these. And as soon as a path deviates from that, we prune them. We didn't use any kind of fixed point computation.
Thanks.
Hi, Adam Dupay, Arizona State University. I was wondering if you could give us a little bit more insight into the annotations. So, I guess my question is before you write one, how do you know if it's going to only fix one case versus the 6% that you got?
Sure.
Were you able to kind of intuit based on the results that you were getting, what annotations to write?
So the general process for annotating something is you get an error report, you spend a while looking at it, and you decide, okay, this is a false positive. And here's why it was a false positive. And if the reason for that had something to do with the data structure, so there are two types of annotations, and we discussed this a little bit in the paper. One that applies to a particular function. So every time you call this function, it runs an annotation on the inputs. And the other is data structure specific. And those tended to apply very broadly. And so if you are examining an error report and realize that it is a false positive because of some data structure invariant, and you know that that data structure is used in a lot of places, like this example, then you probably have good intuition that it's worth spending some time annotating that.
Awesome. Thank you.
Hey, Patrick Hewlin, MIT Lincoln Laboratory. I had one short question and one slightly longer question. The first short question is, are you releasing the tool? Is it going to be? So
it's not released right now. I would like to. There's some dependencies right now on some very old versions of libraries, like OpenSSL, from libs, LLVM, there we go, from 4 years ago. So I need to port a lot of stuff forward, do a lot of cleanup. I would like to. I don't know when that will be yet.
Sure. Okay, I understand. Second question was, do you have any? Have you thought at all, or do you have any directions for further work on what strategies are for reducing the false positive rate? It seems it seems to me at least sort of the key issue.
Yes, that's definitely the biggest shortcoming here. So I'd say ranking may be the best way to go forward. So we have this large number of errors that we report, and sorting through that via some heuristics is probably the most likely avenue to reduce that. There's an issue here whether you want to actually silence errors that you think are false positives, and then you may miss some, versus just ranking them. And then I guess techniques for automatically inferring these invariants, and I think there are some of those out there, more along in the programming language community, may apply well here.
Okay, thanks.